So, hi guys, welcome to the first, I don't know if it's an episode, if it's a podcast or a journal club, but I'm here with Nir Regev and Mike, and I'm Daniel. Soon we will introduce ourselves and what we're planning to do. So I'll start with some background, and this is my background. So I am quite interested in various mathematical concepts for a long time. I guess as all of us since being young. And I did a master's in electrical engineering. And I've been in the industry working with like algorithms or as a data scientist and senior positions close to 20 years soon. Also, I'm into data and also data engineering aspects. So I guess I'll bring that in the future. So that's my background. Nir, you can chime in.
Yeah, absolutely. Yeah. Hi, everyone. So some background about myself. I've been in the industry for the last 26 years, doing algorithm design, signal processing, statistical signal processing, and in the last 10 years, also machine learning and deep learning, quite a lot of those. So everything under the umbrella of AI, I've touched in more than one way. Specifically, my full-time job, so to speak, in my company is doing projects for other companies, and we're doing computer vision and mostly radar and lidar signal processing and algorithms. And I'm also a professor at Cal Poly Pomona, where I teach courses in the electrical engineering department. I also have master's and PhD in electrical engineering from the Ben Gurion University in Israel.
Now I feel like I am underqualified, but I'll try to provide some other aspects. And Mike, you have...
Okay. Okay, hello guys, my name is Mike Erlihson, and I hold a PhD in mathematics from the Technion, Israel, about 20 years ago. And these 20 years I've been working for high-tech industry in many different companies, for many different projects and algorithm positions. And now I'm working as a head of AI in some small company, which is still in the stealth mode. I've done a lot of things. I started from computer vision, then I got to the signal processing, and I taught course in Ben Gurion University, and Nir actually was my student, was one of my best students. And then I worked in Samsung for solid state device, some algorithm for solid state device, and then in NLP, and then in some graph neural networks. After it, I worked for some security company, anomaly detection stuff. I love math, and I love reading papers. I've read about 2,000 papers throughout my life, and in different subjects. In the last 7 years, mostly on machine learning and deep learning. I also wrote about 200 short and long reviews, part in Hebrew and part in English of deep learning papers. And I think it is enough about me.
Yeah, you're almost like a mini ChatGPT of papers. So anyways, why we're here. So actually, I guess all of us are quite active on LinkedIn and post mostly around those areas that we're going to talk here. And for a few years, I felt like there's zero content on YouTube related to like historical papers, where it all started. So we are doing like data science or machine learning or AI, whatever the buzzword is now, but the basic concepts maybe are long ago, but not so long ago. That's one. Second, there's a lot of hidden gems, a lot of intuitions, and it's important to understand where we came from if we want to understand where we're going. So that was the motivation. I didn't see any content. So I said, okay, we should do something. And we know each other mostly from LinkedIn. And then we made this happen. And the motivation is to just go through, let's say, really influential papers that somehow related to data science. Could be more math, could be more, of course, it's all related to math, but more statistical, more probability. Maybe some of them will be also computer science, etc. Right? So, but the idea is to touch prominent influential papers, to have some kind of logical historical progression. So today we're going to go over a really influential paper by Fisher from, as you can see here, 21, called On the Mathematical Foundation of Theoretical Statistics. Sounds like a book. And it's almost a book. It's like 60 something pages. But the idea, again, we won't delve into math and explain exactly the derivations. That's, I hope you did in your undergrad or grad studies. Here we want to convey more like historical context or maybe intuitions, and talk about everything that surrounds the paper. Okay, so that's how I see it. Feel free to chime in, Nir.
Yeah, I want to make some small remark. Why is this paper so important? This paper is on the mathematical foundation of theoretical statistics. Why it is so important? In my opinion, this paper just form a modern shape of the statistics. And why? And so you can ask me. We are talking about papers which influence modern data science and what you call AI. But why this paper, which actually shaped modern statistics, is so important? And you should know it, and it is very important fact that sometimes is neglected, that all modern AI, all these buzzwords and all this machine learning stuff are solely based on statistics, on different concepts of statistics. You have some optimization stuff, but really the most important mathematical subject on which relies modern AI is statistics, and that's the main reason why this paper is very, very important.
Cool. Nir, what are your opinions?
I think that this paper, first, I enjoyed reading it very much. This is stuff that I teach, and also the stuff that I learned during my graduate studies, most. And this is also stuff that I use in my work and use throughout the years, like estimators, detectors, stuff like that. I think that this work lays the foundation of the rigor that is expected out of a statistician or data scientist these days. There were some works before that, but it was all disparate, and I think that Fisher did a good job in connecting the dots for everyone in the research of statistical phenomena as well as probability. And you can see inside the paper all the concepts that we probably know, like likelihood functions, maximum likelihood, the concept of consistent estimator or consistency, sufficient statistic or sufficiency, complete sufficient statistic, the Fisher factorization that we know. It's all there in the paper, but most importantly, there is a survey of what happened before Fisher, and he's also relating his theory or theories to other stuff that was invented before him or realized before him, which is like Bayes' formula. He mentioned Pearson quite a few times, and the Pearson correlation, and very importantly, the Pearson method of estimation, which is the known method of moment estimator.
He talks about it, he compares maximum likelihood to method.
Right. and also the student distribution that was, I think, just 15 years before, 16 years before introduced to the world, which is a story by itself, a nice story actually, coming from the Guinness Brewery, from all places. So yeah, that's in a nutshell what I think about this paper.
By the way, can you, when I do screen sharing, can you see yourself or just the paper?
No, I can see all of us and the paper.
Yeah, and I can see you.
But do you see
Myself.
ourselves in the screen share?
Yes.
Yes.
Ah, okay, perfect. Because I wasn't sure if it's just recording the PDF or all of us as well.
I think Zoom is recording everything.
Oh,
yeah.
Okay, cool. I wasn't sure. Again, I'm a noob at doing
Okay.
stuff.
And I want to end a very small observation about maximum likelihood. We are trying to connect our papers we are talking about with the AI and machine learning and the modern stuff. It is very important to, as Daniel said, it's very important to know our history, because if you don't know the history, you can't build a good future. Why this maximum likelihood is so important? What happens when you train our models? What we are doing? Actually, almost all models which we are training on some data sets, actually we are trying to fit some neural network to maximize our likelihood. And Fisher was the man who actually defined what is likelihood, what is likelihood,
Yes.
and what is maximum likelihood. And that's why this paper is crucially important.
Cool. I agree with you all. I'll add my observations. I felt a few things already. First, that I lack some language. So it's been like 100 years, and some of the things that we used to call in one way today, he used different words for them. At beginning, we're gonna see it now, if we start, is using like inverse probability.
Yeah.
It means by that like Bayes theorem or Bayes inference. So that's first. And there's other concepts, let's say he uses various different names a little bit. So that was first, to like understand the language. Second, I felt the paper is more like on the philosophy of statistics, because it begins, like if we go and see it, with the first chapter, the neglect of theoretical statistics, right? So he talks about how there are so many open problems, nobody really formalized things, and then he needs to formalize, right? And needs to define the things that we use in statistics. So it's like meta, it's the philosophy, what we're actually doing here, which is really cool. That's why I felt like, there's some math, but I don't really care about it. I just want to understand the motivation. So I think we should start by actually reading parts of the first chapter, because like this lays the foundation of his critique and what he tries to achieve with this paper.
One small observation before we are starting to read. You should understand that theoretical statistics exist before Fisher. This field existed. It shaped the modern statistics, but the field existed, and there are some important tools like Pearson criterion and his square criterion, which we are currently using, although they were invented 130 years ago. But the Fisher contribution, the most important contribution, is in introducing a new concept and then formalizing the old ones.
Yes.
Cool. So again, the first chapter we'll dive deeper. I think the other ones will go faster. The idea is to get up to 40-45 minutes per paper. So he starts with saying there are several reasons contribute to prolonged neglect in the study of statistics, and the theoretical parts has fallen behind in some sense. The basic principles of the organ of science are still in a state of obscurity, which is also interesting, right? Again, it's 102 years ago. I'm not sure today scientists know really what science is, but that's a different discussion. And he says here, in spite of the immense amount of fruitful labor, which has been expended in its practical application, there's still the obscurity. And he says the anomalous state of statistical science is strongly exemplified by a recent paper. There's a paper that says the fundamental problem of practical statistics, which I didn't read, but I infer from what he says, it's some kind of critique of Bayesian probability. Yes. Right? That's what he says here. So I guess prior to this paper, because again, Fisher is considered the father of frequentism, right? So prior to this paper, in a sense, most statisticians were Bayesianists. You agree, Nir, with that claim?
Yeah. I mean, it was a prominent concept. So if you scroll down, just before he goes to chapter 2, he said it is this last confusion in the writer's opinion, which is him, more than any other, that has led to the survival of the present day of fundamental paradox of inverse probability, which is Bayesian.
Which is Bayesian probability, yeah.
Yes, which like an impenetrable jungle arrests progress towards precision of statistical processes, concepts. And I think that this small paragraph summarizes his opinion of that the statistical world, in terms of mathematics, has to progress and use other tools as well, and not only the Bayes law.
Yeah, I think it's here.
It's on page 311 in the bottom, just before section 2.
Yeah, I'm sharing. You can see in the
over there. Yeah.
I think he's trying to add some new concepts. He's not calling to neglect the older ones. He thinks that these concepts should live one near another together. And so basically the Bayesian approach is very popular today, together with the frequentist approach. But here in this paper, in at this moment, 200 years ago, there was just one approach, the inverse probability of Bayesian, and Fisher is trying to introduce a new one, which somehow I can call it complement this Bayesian approach.
Exactly, yeah.
Exactly. I would just like to add something that took me years to, let's say, internalize, because nobody really taught me in statistics, but there is, in a sense, a metaphysical difference, meaning in the way how Bayesianists and frequentists perceive or think about the world. Okay, so it's not just a difference of mathematics and for formalization, but also how they think. And you can see this critique of Fisher throughout the paper. So I would just give it in a few sentences, like my understanding. Let's assume we want to measure the flux of some star that is far away. Okay, and we have a detector. A frequentist will say there is a precise value at each moment to this flux. And then we measure some data. The variance or uncertainty comes from our measuring device, maybe the medium that adds some noise, etc. Right? I see Nir smiling from signal process perspective. But the value itself is something which is deterministic. Yeah. There is a value out there. That is why we cannot ask about the probability of that value. It's undefined. It's because it's deterministic. It's something. And this is why Fisher, at least as far as I can tell, thinks that Bayesian theory or the theorem itself is a problem, because you cannot really have a prior, right? And that's where Bayesianists come in and say, no, this flux of a star, there's a probability distribution. Yeah. Now, maybe there's a mean and variance, whatever, but it's not one single value. And that's why they can use Bayes' theorem. and
Yeah.
frequentist in a sense cannot. And this is why, in a sense, he added or introduced the maximum likelihood, and we'll get to that. And to me, this is like a metaphysical difference. Are the things out there unique with specific values, or are they like a distribution of probabilities? Okay, and without going more than that, you can add a few words, but this is how I see it, and I felt it through this paper.
Right.
Make sense?
Yeah, makes sense. Makes sense completely. And this is exactly the, I think, the distinction between when we teach or learn the estimation theory course, or even I think mathematical statistics course in the mathematics department, which I also took. There is the concept of parameter estimation that is deterministic, which is mostly maximum likelihood. That's or method of moments and other stuff. And there is the non-deterministic or probabilistic parameter estimation, in which we assume some sort of a prior probability or prior density or mass function to this parameter. So for example, I can give you an example from the real world. In radar. In radar, we have a concept called, or even in LiDAR, RCS. Okay, it's radar cross-section. In LiDAR, the equivalent term is reflectance or reflectivity. Now, if I define an object, this object has a deterministic radar cross-section. How the radar will look at it. What's the cross-section or the projection of this mass onto the radar beam. Okay? But in reality, not because of noise, but because targets are moving in space, they're not stationary with respect to the radar. If I present it like this to the radar will see something else. And if I start rotating it because it's moving, or like an airplane traversing space, we will see other projections of the same volume onto the radar beam, so to speak. And it has a probability density function, even though the deterministic
it's
RCS,
deterministic. Yeah.
Yes.
I get that.
Even though, so we can assume something about this to help us determine which object it is. And that's where we use also Bayesian statistics or Bayesian estimation stuff.
Yeah, Bayesian too, because both what you're trying to estimate, like the parameter, and also Fisher defines it as parameter. It's the something, it's the true value out there.
Exactly.
Compared to the estimates that we do to try to estimate this parameter, which is deterministic.
Yeah, exactly. But still, there is very important thing for me, and I think I realized that not when I did my undergraduate studies. I think I realized when I started to learn and to dive really deep in statistics. For me, you know, in Bayesian statistics, you are trying to estimate a distribution, okay? But in frequentist statistics, you try to estimate a parameter. But how do you estimate this parameter? You are using some kind of statistics. And what is statistics? This statistic also has some distribution, you know. So for me, the fundamental difference between Bayesian statistics, one more fundamental difference between Bayesian statistics and frequentist approach is that in the Bayesian statistics, the parameter itself is distribution, and in frequentist we also have the distribution, but with distribution, with distribution, we are trying to estimate some deterministic value. So in both cases, we have distributions, but they have some different meanings. You know, this is the way I understand this stuff.
Yeah, actually, there is a lot of, for example, Kalman filter. Okay, Kalman filter is a Bayesian approach for estimating parameters, and it's what we call the minimum mean squared error estimator, we use the a posterior statistics or probability density function to take the mean of these and say, okay, the parameter is most likely to be on the mean. Okay, but we basically take the mean of the over the parameter we want to estimate, but the mean is taken over the posterior function and not the likelihood function. And that's in terms of parameter estimation, these are the differences. Because also in maximum likelihood, I can estimate the maximum likelihood. I can estimate the likelihood function per the parameter, and then you have a distribution per the parameter, not per the measurements. I think you can do both in the Bayesian approach as well as the deterministic frequentist approach. And I think that what Daniel said is also correct, which is more philosophical, and I lack a better definition than just to use the word philosophical. Daniel used metaphysical that I don't fully understand.
It means your assumptions on reality, right? Your assumptions on reality are not physical.
Got it. Okay.
So they're metaphysical. At least in philosophy, metaphysics, that's the study of your assumptions and what's beyond physics.
Yeah.
I do have background in academic philosophy, by the way. I wanted to say, look, whatever we're talking about, it dovetails nicely to the second chapter, because here Fisher actually defines, in his opinion, what statistics is. So I'll read you the sentence and tell me your thoughts. In order to arrive at a distinct formulation of statistical problems, it is necessary to define the task which the statistician sets himself. Again, you see, this is like meta statistics. What we're trying to do here, briefly, and it's in its most concrete form, the object of statistical methods is reduction of data. Okay? I says a quantity of data which usually by its mere bulk is incapable of entering the mind, is it to be replaced by relatively few quantities which shall adequately represent the whole, or which, in other words, shall contain as much as possible, ideally the whole of the relevant information contained in the original data. So this is really deep. Tell me your thoughts. Do you agree, disagree, make sense?
I will actually try to connect it to the modern machine learning. We love to talk about some latent representation of the data. So what is this latent representation of the data? So what is this purpose of building some kind of encoders which we build in order to build some low dimensional representation of the data? What are these low dimensional representation of the data? This representation should include all the information which we have in the data, but it should be much smaller than the data itself. And then you think about it, it is really what is written in this paragraph. It is just for me, it's just amazing. And I've read this paper, but somehow I missed this paragraph, and now it made my eyes open, widely open, you know.
So embeddings is statistics?
Yeah. It makes sense. So then you think about large language model. This large language model contains all the data which you have in the internet, but still this model is much smaller than the whole internet. The whole internet is exabytes of information, and this model is 100 gigabytes, maybe 500 gigabytes, maybe 2000 gigabytes, but still it is much smaller than the internet, but it still has kind of all knowledge which you have in the internet, how it is done. In the training, you're just training your model to compress the data in the most effective way, which is this is the way I see it.
Yes,
cool,
100%.
I like it. Nir, your thoughts?
Yeah, 100%. I also highlighted this, Daniel.
Okay. Now
I didn't read that. I didn't know it.
because this is a perfect. I think this is a perfect definition, because this is what we do in parameter estimation. We take a lot of data, it can be millions of points, and reduce it to the mean and standard deviation or variance of a distribution, and that's it. Okay. so we basically compress millions of points into two. Okay, so that's just an example. It can be more than two, obviously. In machine learning and deep learning, it can be also millions. And then we're talking to compressing billions or trillions to millions. Or you get what I'm saying here. But he also in this paper he also presents the Fisher information, which is according to this paper the only information and complete information that is relevant to the estimation.
Not in this paper.
Not in this paper?
No, in this paper I saw when he talks about information, he says that if there's two estimators, right, trying to estimate this parameter that is out there, the true value. So if you take one and you do conditional probability on the other one, you don't get better estimator. That's how he defined information, by conditional probability. So I didn't see here the Fisher information.
Yeah, I think that he defined, also gave examples here, that the efficiency of an estimator is the variance of the proposed estimator divided, the Fisher information divided by the variance of the proposed estimator, which makes sense because we know that the minimum variance or minimum mean squared error, MSE, or the Cremera lower bound is 1 over the Fisher information. So this ratio makes sense because it's basically, it's not saying it in so many words, but it basically says everything you need to know about a data is contained in the Fisher information. That's the bound for the information. You can't gain more than that. And
interesting. So I missed that. I saw that derivation, but maybe we termed the term Fisher information came later, or did he actually said it in the paper?
I think he did.
Okay, so then I missed it. I saw discussions of information, but but I didn't dive deep in the math.
It can very well be that I, got down the rabbit hole of his references, and my brain is spitting out something from another paper of his. But as far as I remember, yes, the concept of efficiency is well defined here, and efficiency is the Fisher information divided by.
You're right. But I think he didn't say. We'll see soon, he defined maximum likelihood, but he didn't say, I'm defining a concept of information here. He just used that as part of talking about the efficiency.
Okay, yeah, we'll scroll down and get to it.
We'll see. So I just wanna give my view on this, let's say, paragraph, what is statistics? Actually, I disagree, but again, I have in a sense, 100 years I'm later than Fisher. Because I think statistics, here what he talks about, it's really narrow. In my view, if you ask me what statistics is assuming there's data, whatever that it is, at hand, you want to ask a question about the data. Could be, again, whatever question you want, natural language question. Then you use statistical tools to answer to those questions. That's like science in a sense, right? So maybe my definition is broad, maybe it's more like scientific in a sense, or maybe it's more data science than statistics. Again, we won't go in this rabbit hole of debating that, but that's how I view it, right? And again, maybe you can say this is math, but math is also other abstract stuff that are a priori unrelated to data, right? So that's why statistics is really like empirical. That's my view. Okay, so that's why I wanted to be contrarian here. Okay, so let's continue. So we'll make some progress. And this is also important. I want to continue because again, this shapes how people study statistics today when they study courses, right? It says the object of statistics. You see it?
I see it, but can you zoom in for me?
Yes,
and for
I'll zoom in. Yeah.
Need glasses? Thank you.
I don't know. It's jumped to, I don't know which page. Oh, okay. It says here, this object, meaning the object of doing statistic, is accomplished by constructing a hypothetical infinite population, which the actual data are regarded as constituting a random sample. So this is what everyone who studies statistics, they say, okay, there's a population, which could be something. And again, if you're Bayesian, there's a distribution to each value or each parameter there. And then at the end, empirically, we have only a small sample. I think the important part for me in this paper, and that's when I didn't see when I studied that, he calls it hypothetical. I think that's important because this population is not like, okay, all the males that are between 40 to 50 and I'm doing, you know, what's their height and I do some kind of distribution. It's some kind of hypothetical, maybe infinite. So it's a mathematical construct.
Yes. Yes.
This hypothetical space. That's important to understand. And what's real, or at least what we have, is a random sample out of it, which is the actual data we work with.
Yes.
I will, okay.
You can add, Mike.
Okay, I'd like to draw a little connection to the modern machine learning. We are training our data on data sets, and almost every paper on machine learning starts with suppose that this sample was drawn from some distribution. And this is exactly what I said. But this sample hasn't been very small. Now we have huge samples, sometimes of hundreds of millions and maybe more samples. But still, this concept stands. You are drawing it from some infinite population, and you have your data from this infinite population, and you are trying to estimate the distribution of some parameters, or maybe distribution itself of this infinite population. Its concept is very, very important.
Yes, agreed. And I think he alludes to either, I think all this paper, almost all of this paper focuses on contiguous distributions, which obviously are infinite in population. But these also holds for infinite discrete distributions, this concept. And I think it, even in data science and machine learning of these days, AI, we have sometimes billions, trillions of examples, but still it's finite, exactly like you said, Mike.
Yeah.
And we basically train the model to compress all this data to parameters that we can then take these parameters, plug it into a distribution, and generate new examples, for example. So.
And interestingly, let's talk a couple of sentences about supervised learning. What do they assume in supervised learning? For example, we are trying to build some classifier. We have some types of animals in our picture, and almost in every paper, we can. It is written something like, assume that we have some function which takes a sample from the distribution of images and maps into the distribution of type of these images. And this is just a simple extension of this concept, because you still have your finite sample, but now instead of estimating this distribution, we are estimating this mapping from this complex image distribution to some set of classes. But still, the concept, remarkably, the concept still stands.
Yes.
Got it. Let's continue to the third chapter. The name is The Problems of Statistics. So now, after he defined in the previous chapter what he thinks statistics is to him, then he says, okay, what problems statistics is trying to solve? It's not like what's the problem in a negative sense of statistics. That's a different discussion. It's which problems we're trying to solve here. Then he did like 3 groups, or let's say he classifies them into 3 groups, and he says even the problems which arise in reduction of data. So to him, it's a synonym for statistics. First, problems of specification. Okay, so this is the choice of the mathematical form of the population. So again, we got a hypothetical population, right? And we need to give some assumptions or assume some kind of model because it's an abstract entity. That's first problem. This problem of specification. Problem of estimation. Okay, once we did that and we got empirical data, we measured something. Now we're trying to estimate, he says, estimate the values of the parameters, because again, we talked about this, that's deterministic value of the hypothetical population. And so that's second, that's estimation. That's a second problem statistics is trying to solve. Third problem is a problem of distribution, meaning now how the data that we measured, how it's distributed. Again, we do assumptions here, we have maybe some models, etc. Nir, I'm asking you, how does it align to, let's say, what you do with more like signal processing stuff? Is there analogy here, in your opinion?
I think so, yeah. I mean, for number two, of course, yes, we are estimating stuff all the time. In LiDAR, you want to estimate the XYZ of the target, right? In radar, the range, the Doppler, everything there is an estimation, theoretic approach, everything that we do in radar and LiDARs. And I would argue also in computer vision and even modern computer vision, I actually treat neural networks as estimators. So it doesn't. Okay. Yeah. So
explain that. That's an interesting claim. What do you mean by that?
I mean, we're estimating the matrix of the weights, right? If we use the minimum, the mean squared error criterion in terms of objective function, then we are doing some sort of a MSE estimation or minimum MSE estimation. If we are maximizing or minimizing KLD, like you posted quite a few times on LinkedIn.
We're gonna go over the paper in the future, so just it's foreshadowing for future episodes.
Likely with
KLD is in the pipeline.
I know. I figured that much. And yeah, so estimation problem 100%. The first one we also do all the time. So we look, even in data science, we look at the distribution or the histograms of processes or of data, and we try to figure out which distribution function will model this with the least error. Okay.
So I'll try to recap what you said. Tell me if I got it right. So when you train neural network, you look at the weights as the parameters. So out there in the world, there's a parameter, which is the true value. Now, when we have data, and we're trying to estimate it, and that's what we do in neural networks.
Yes, exactly. All the so-called machine learning algorithms, like linear regression. This is like a trivial example. This scores estimation. It's the estimation of the parameters of the line or the hyperplane. Okay, so it can be 1,000 parameters. It can be 2 parameters. It doesn't matter. It still is an estimation problem, and that's how I view machine learning. Because I am a little bit biased, I learned the estimation theory and detection theory and statistical mathematics before I got into machine learning. So when in my work before my graduate studies, we employed machine learning algorithms like, for example, GMM or SVM, without calling it machine learning at all. We call it statistical algorithms back then, like 20 years ago. And yeah, so for me, it was all the time an estimation problem or a detection problem, which is also a kind of estimation problem, because you have to estimate which class, 0 or 1, is there is target or there is no target in radar, for example.
Yeah, and a small remark, there are some Bayesian approaches to training neural nets as well. These approaches are not very popular now because these networks are hard to train, and it is we can do most of the stuff with our lovely frequentist approach, but still this branch of deep learning, at least 3 or 4 years ago, I was seeing some papers about it. Now it almost disappeared, but it exists.
Yeah.
Thanks, Mike. And thanks, Nir. I like your views. And let's proceed. So I move to the 4th chapter, and he says, like, part of chapter 3, that okay, there's the problems that statistics are trying to solve: specification, estimation, and distribution. He talks a little bit about specification. He says, okay, future research should do it. Then also about distribution, we should do in the future. And now he says, I'm gonna focus on estimation here. Okay, and that's why the next chapter is the chapter of estimation.
Yes, and
meaning we got data,
go
we're trying to estimate the parameter. Sorry, yeah, Nir.
And you see that also connects to what I said earlier, because you see here what we use in machine learning, like objective functions, right? That we want to minimize. So the first one is the absolute value distance. The second one is the mean squared error. And we use probably without the square root, but it's the same, essentially. And that's just connecting to me viewing machine learning and deep learning as estimation problems. Sorry for cutting you off, Daniel.
Cool. I see what you're saying, and I think as I delve more into statistics, because again, part of my motivation, I felt like I didn't get a good grasp of it when I was studying, I totally moved to that direction as well. So it's interesting. So anyways, this chapter here, he says, okay, now we're looking at estimation. Okay, so we have data, and I'm trying to understand or infer or estimate something about a true parameter out there. And then he breaks, he like gives a criteria, okay, for what an estimator should be, in a sense, or what is a good estimator. I don't know if that's how he defined it, but he said, okay, first, estimator should be consistent. And it says somewhere here, criteria of consistency. So it says, it means that when applied to the whole population, the derived statistic should be equal to the parameter. Meaning, if I have the data of the whole population, my estimator and the true parameter should be the same. It's called consistency.
Okay.
No, you continue. Ask.
I wanted to ask something. Yeah, I wanted to ask Nir. I don't remember it. We're talking about convergence here. For consistency, if your population is tending to infinity, then your statistics, your estimations should converge into something. But you know, in probability theory, there are several convergences. I don't remember where it's weak convergence and almost sure convergence. What convergence we are talking about here in this specific case?
Well, this is convergence in probability. So the formal definition of consistency is the lim n goes to infinity. The probability of, open brackets, the absolute difference between the parameter which is dependent on this n that goes to infinity, as we estimate it from more and more samples, minus the true value. Will be probability will be less than epsilon with probability 1. So this is the type of convergence that consistency is talking about, and this is the weakest criterion for estimators.
And Nir, I have a hypothetical question. For example, if I replace this the weakest convergence by almost sure convergence, what do you think can happen? How this consistency estimators will change? What it will change, if either?
This convergence is almost surely convergent. So in other words, we say that when n goes to infinity, the estimator will reach the parameters almost surely.
Okay, okay.
So this is the same type of convergence.
Okay, okay.
It's not convergence. It's not necessarily first an unbiased estimator. Like it's unbiased only in infinity. So it's asymptotically unbiased. Okay, unbiased means that the mean or the expected value of the difference between the true parameter and the estimator is 0. Okay, so in the mean it converges to the true parameter. So this is unbiased is stronger than this criteria. So this is the next. This is the next. By the way, both of them are saying nothing about the error.
Yeah.
Okay. Both converges almost surely and unbiased, which is in the mean. They're saying nothing about the error except that the estimator's distribution is centered around.
That's exactly the next sentence. So he says here, considering of the above example, we suggest a second criteria. Okay, yes. So after consistency, we have a second criteria, namely that in large samples, when the distributions of the statistics tends to normality, that statistic is to be chosen which has the least probable error. And here again, this is language. When he talks about probable error, he talks about variance or square error in a sense.
Yeah, mean square error. Yeah.
Mean square error. Yeah. So if we have various estimators, we want an efficient one. It's the one with the least mean square error.
It's the one with the least mean square error. It's also the one that is unbiased. So two conditions occur in an efficient. But
he didn't talk about bias here.
Yeah, he didn't talk about bias per se. That's right. But the modern, he also find efficiency in a asymptotic way here in the paper, which is not the common definition of today.
Okay, cool. That's important. I didn't know that.
There is asymptotic efficiency and there is efficiency. And if efficiency are estimators that are meeting the primary or lower bound, which is to say they're unbiased and they have the minimum variance estimator.
And it feels that this efficiency and consistency also define implicitly the convergence rate of the expected mean of this estimator to the true estimator. We are talking about normality here, so it is square root of n, or if we are talking about SSD is square root of n.
Yes, absolutely, yeah. In the standard deviation, it's the square root of n. The variance is 1 over n. Yes.
Yeah.
So in the normal case, yes, definitely. So if we will, I think it gives example down there. If we get to it today, in which the Fisher information as well as the variance, which is 1 over the Fisher information, is dependent on the number of samples, and sometimes it's dependent quadratically on the number of samples, sometimes to the power of 3, and sometimes just 1 over n, like in the normal case for the mean. Yes, so this is all very interesting. By the way, when he says statistic here, he means any estimator we can derive from the
exactly. He talks about estimators.
Yes. Like basically, it's a function of the data. That's it.
Yeah.
Arbitrary function of the data.
And the last, now there's the third definition of an estimator. It says to complete the criteria suggested by our work on the mean square error is that the statistic chosen should summarize the whole of the relevant information supplied by the sample. And again, now he talks about information. This may be called the criteria of sufficiency.
Yes.
And I think this is very important. I'm trying throughout all our video. I'm trying to connect it to more than machine learning. And then I read it. I thought about compression. So what we are doing with our latent representation, we are trying to compress our data, and I think that the ultimate latent representation, the most effective A latent representation is a latent representation which compress our data but preserves all the essential information in our data. And in this relation, it can be called sufficient estimator. This way I see it.
So like sufficiency is compression in your
the ultimate compression is the most effective compression.
Okay.
This is more efficiency, I think.
I'm scrolling through math.
Yes.
Avid readers of the paper are welcome to check that he didn't have any mistakes here. And I'm moving to the next chapter. Like, think about it. This is 100 years ago. How he like drew it by hand or something, you know, those plots. I have no idea. Like, maybe he had some tools, you know, like
then my dad did his PhD, but it was 45 years ago. He was using printing machine. So maybe, but it was in 1970s. So it was 50 years before Fisher. Maybe there are some printing machines, you know.
And here, the next chapter starts with, again, we continue with sufficiency, like we can call it compression. He tries to formalize it, okay? And he calls it method of maximum likelihood. Although I am not satisfied as to the mathematical rigor of any proof which I can put forward to that effect. Okay, so he says, like, I didn't finish everything, you know, so I might have mistakes, but bear with me. Readers of the ensuing pages are invited to form their own opinion as to the possibility of the method of maximum likelihood leading in any case to an inefficient statistics.
You know, you don't see stuff like that in modern papers. And
so that's why it's beautiful. Let's say like humility.
Efficient.
Excuse me, Nir?
Again, listen, for my own part, I should gladly have withheld publication until rigorously complete proof could have been formulated. But the number and variety of the new results which the method discloses press for publication. And at the same time, I am not insensible of the advantage which occurs to applied mathematics from the cooperation of pure mathematicians. And the cooperation is not infrequently called forth by the very imperfections of writers on applied math.
And look, this stuff was written by one of the greatest mathematicians of the 20th century. You know, you never see such stuff in modern papers, which in 10 years, nobody will know them. You know?
No, it's true. It's true. These papers are rare. That's the amount of papers that is coming out today is a dime a dozen. And most of it is garbage. Sorry.
Totally agree.
And this kind of self-critique is, and the importance of this is not lost on me. And actually, I completely agree with the self-observation and self-critique he's posing here. And we know, by the way, I didn't know it at the time, but we know now that maximum likelihood is only efficient asymptotically under certain conditions. For some distribution, for example, Gaussian, it's also efficient locally, not asymptotically, like always efficient. But it's not the case for all maximum likelihood estimators. And I would argue that the maximum likelihood estimation we're doing in deep learning networks is not efficient. It's only asymptotically efficient. And it's good that we have a lot of data to train on because
but maybe not enough. Maybe we're not asymptotically.
Sure, that's also a problem. We don't have enough data, right? How many times did you hear that, Mike?
Many times. We have exabytes of data, you know, now.
Exactly. Yet we assume that it's infinite, and that's the gap that we have in estimating and the performance of machine learning algorithms as well as deep learning that are not optimal in the sense of efficiency.
So I just want to introduce, again, we won't dive into the math, the maximum likelihood, what he says and how he defines it. So he defines a function of all the probable estimators. Sorry, all the probable, sorry, given the data, we have data. And then we try to go over all possible parameters through values out there, and then see which one maximizes our data.
Yeah.
Okay. He says the method of maximum likelihood consists simply in choosing that set of values for the parameters which make this quantity a maximum. And then he talks about how it's different than Bayesian or Bayes theorem. Okay, because it sounds similar. We're doing this like we're changing. Okay, given the data, what are the possible parameters? So it seems like parameters have a distribution, but frequentists assume parameters have a fixed value. So he talks why it's different, and he says here also that this maximum likelihood is not probability. Like it's not differentiable. It doesn't sum to one, etc. He talks about it. But he says it's still really pragmatically useful for us.
And that's why it is called likelihood. What does it mean, likelihood? How likely is to get our data? So we have our data, and what likelihood just measures how likely, under some assumption that we assume about the distribution, how likely we can get this data. It is very intuitive assumption.
Okay, so I'm scrolling through, and I think here maybe he talks about like Fisher information.
He gives examples here. For example, he derived the maximum likelihood for in this where you were in this page up there. He derived the maximum likelihood estimator for the Bernoulli distribution.
That's right, like a coin.
Yep, like a coin flip. Yeah, and we see that it's also the relative frequency that we use all the time in Monte Carlo simulations.
But usually Monte Carlo are not for Bayesian methods.
No.
Okay, cool.
Not all the time. No.
That's true, because here I also want to go over all different possible values of this parameter that is out there.
By the way, Monte Carlo is one of the topics I think we need to record some video about.
A paper.
It's very interesting.
I'll gladly go over the Monte Carlo paper. It's also such a lovely name. Why it's called Monte Carlo? Was he like sitting in Monte Carlo and when he was doing that? Like I don't know the story behind that.
It's the casino. It's the casino.
Yeah.
So, but this is the motivation behind the name of the paper.
Yes.
I think Los Alamos project. There was some physicist, and his uncle was very heavy gambler, something like that. I don't remember. But it is somebody's uncle being heavy gambler in Monte Carlo. Yeah.
Okay, so I think we covered the important topics, because again, then he gives examples, derives, determinant of stuff. Again, I didn't follow that when I was reading. I think the next step is the summary, as far as I remember. Let's see. What am I missing? If there again, look at this. I think he drew it behind.
He's analyzing the method of moments, and he's showing why for the Gaussian distribution the method of moments is efficient.
By the way, Nir, is anybody using the method of moments today for some real problems? No.
Never. I never used it.
Okay, let's see more plots. Again, this is 2D. Like each plot now we do in 2 seconds, and we also like curse. Oh no, in Python, you know, it moved here. Like Plotly is crap, you know, and he drew it by hand probably for a week.
Yeah, no, ChatGPT is writing all the code for you. You just define your problem, and I'm not wasting time on this PyPlot. I just wasting time on building my prompt efficiently.
Exactly. Exactly right.
Okay, we converged. Prompt engineering in statistics, done. I still doing some edge cases. Let's see what else is important here, in my opinion.
How much time takes to write 60-page paper in the 100 years ago? It's kind of crazy.
Probably.
Yeah. Okay, so we're in the last chapter. And I'll read a few of the words he said. Again, he talks about the problems, the adequate distinction, in the inverse methods, which is Bayesian theory. What's else important? Talks about each. No, I think there's.
I have a small question
Yeah.
here. He's
Okay,
talking
let's
about
have
specification. One small question. He's talking about specification. Is it about defining an underlying distribution for maximum likelihood? It is about something else.
Specification is what we assume about the population, the hypothetical population, right?
Meaning the distribution. The distribution, it depends on your data and your parameters, which you are trying to estimate.
Yes.
Okay.
That's what I understand as his definition of specification.
Okay.
We can find it quickly. It's chapter number 3. Let's go.
Item number 1 there.
Let's go up.
2, 3, 1. Yeah, I understand.
Going fast enough. My page up doesn't work. I don't know why. Maybe because we're recording. Let's see.
He didn't have a page up to use.
Yeah.
Almost. That's estimation.
This is consistency now, specification. Yeah.
Yeah, we're gonna go chapter up. Why am I missing it?
That's it. That's it. You passed it. You passed it.
Ah.
You passed it. Go down. Go down. Go down. Go down.
Oh, here.
Stop. Number 1 here.
Yeah.
Yeah. This mathematical form of the population. This is another name for the distribution, which depends on some parameters we are trying.
He defines the distribution as number 3.
Oh, that's different. That's different.
This is statistics. This is not. This is distribution of statistics. This is
that's right. Number 3 is the distribution of your data. Like
and see in 1, this is also about compression. Yeah, we are talking about describing the whole population, which can be very high dimensional, with some distribution which has much less parameters than the number of dimension of your data. You know, it's also compression. So we are trying to find some compact representation of our data, and the more I think about the estimation, I in myself, in my brain, I converge to compression. I don't know why, but you know, this is my way of thinking about it.
Yeah, you are an example, Mike. For me, you are a mentor and also a role model, because you jump from signal processing, communication theory, OFDM, to compressing algorithms over Galois fields, and then to machine learning, deep learning, and LLMs. I never seen anyone in my life doing that. So I think that's why also you think compression, because you dealt with it a lot.
Yeah. By the way, there is very interesting paper and very interesting lecture of Ilya Slutskever from OpenAI about this connection of compression and the Kolmogorov complexity, which we can also discuss in our next episodes. And there are a couple of very interesting papers which are rare paper. You know, almost all our papers we have best performance of the benchmark X and benchmark Y, but there are some very interesting papers. I think two of them I reviewed about the role of compression in machine learning, because I think the role of compression in machine learning is much underestimated, because all the machine learning we are doing is almost compression. You know,
100%. It's a lossless compression, but it is compression. Sorry, it's a lossy compression, but it is compression.
Yes. All these embeddings, as I already said, and it's very important observation. All these embeddings of your data, of your text, of your images, of your videos, of your audios, of your DNA sequences, you're just compressing it because your data is too high dimensional. You can't handle this ultra high dimensional data, so you need to compress it. And how to compress it? This is all machine learning about.
Yeah. Even simple algorithms like SVD, PCA, whatever machine learning is terming in these days, compression.
Yeah.
Right.
Yeah. Exactly.
Yeah.
That was lovely. Probably next paper will be about some probability and Kolmogorov. He wrote some nice papers 10 years past Fisher, the one we talked about here. So probably that will be the next chapter. Feel free to offer other ideas.
Yeah.
And
I think Kolmogorov complexity is a bit involved concept. I think our transition should be a bit smoother. So let's talk about.
No, I meant papers by Kolmogorov. Probability that he wrote 10 years prior. And,
yeah.
Okay, that's what I meant. He has some few influential papers. We should choose like the most.
Fisher reference these papers also here in this paper. Fisher references Pearson, Kolmogorov, and the pseudonym student, which we're familiar from the T-student distribution. I want just to add two finals, maybe comments for this paper. He shows in the examples what we all know from statistical theory of the sample mean and the sample variance estimators, or the reduced form of the sample variance estimator, which are efficient in the Gaussian case. So it's in the Gaussian case, the best estimators we have for the mean is the sample mean. And the best estimate we have for the variance, when we know the mean, is the sample variance, in which the mean is given. So the two basic observations from this paper.
And again, when you say the mean of the distribution, you mean again of this hypothetical population? It has a parameter which is out there.
Yes.
And now we're trying to estimate it.
Yeah, exactly. From the first bullet on your screen.
Again, I'm trying to see that I follow your logic.
Yes. So if we assume Gaussian distribution, normal distribution, the best estimator for the mean, the mean is defined as the true expected value of the infinite populace, is the sample mean, which is the sum over the number of elements, what we call average. Which is interesting because it's not true. I mean, it's true in the like the law of large number will prove that it's true in the asymptotic sense for everything, but in a sense of only you have a few samples or examples, limited amount of examples or samples or data. It's efficient, which means it has the minimum variance, and it's also unbiased estimator always, not asymptotically. for the Gaussian case.
In our case, as Mike said, efficient, it means it compresses the most information.
Yeah,
Exactly right. Yeah.
To the most extent.
Yeah.
So you just need to compress your data.
Yes. Yes. By the way, PCA does the same thing, right?
Yeah.
It breaks the data or the data to the maximum variance directions, right?
Yes,
Maximum variance,
exactly.
Maximum variance is the minimum required information.
Yes.
That's it.
And kernel PCA does it just add some non-linearity, some kernels to it. So this is because, and this is exactly the reason why I am always thinking about compression, because this is just what we are doing now in machine learning.
Yes.
Perfect. So thank you. It was a pleasure. And hopefully next week we'll have the next paper out.
Yeah.
Amazing. Thank you, guys.
Yes. We will try. Our best.
And we will succeed.
Yeah.
Are we going to request the users the usual subscribe and like, or are we never going to request that?
Yeah, why not? I'm a noob here, so I don't know.
Right now.
We will ask, maybe we will get some. I'll try to share it on my LinkedIn. I have some 50K followers, and I have some on Twitter. So let's try to ask for some likes. Maybe we'll get it.
I'll send it to my mom.
Yeah.
Deal.
Yeah.
She'll press like.
Yeah. Guys, thank you very much. I enjoyed it.
Thank you very much.
Have a great day, everyone.
Bye-bye.
Bye-bye.
Bye-bye.